So when a conductor moves and in such a way that it cuts through magnetic field lines, an EMF is induced across the conductor. And if that conductor is part of a circuit, it can set a current in that circuit. But that current will have a defined direction. It will be moving in a certain direction, and we can also predict the direction of that current. But what if instead of a wire-like or rod-like material cutting magnetic field line, what if a a surface-like thing is having a change of magnetic flux around it? It's not a normal conductor. It is not. It is the surface is made of a conductor, but it is not a wire-like conductor. It is a surface. Now, when a surface has a change of magnetic flux around it, we can have points of higher potential and lower potential on that particular surface. For example, this is a fixed magnet. This is a strong magnet, and a disk is moving nearby this one. This is a strong, permanent magnet, and this is a copper disk, thick copper disk. So what will happen when this disk will be moving? It will be have a point of high potential and, for example, Q is a low potential point. So what will happen? We will be observing currents that will go from P to Q. So we will be observing currents on the surface, maybe from R to S. Okay. So we can observe currents going from R to S or S to R, P to Q, or there will be currents on the surface. Such currents are called eddy current. When magnetic flux changes near a flat conductor surface, that surface develops points of higher potential and lower potential, which can cause currents on the surface. Such currents are called eddy currents. These currents are the cause of increase in temperature. Such currents in recent time, these currents are used in industries to produce high temperature, and they can be used for melting and heating metals. So eddy currents are used very commonly in industry to produce uh, heat. Some stoves also work on this phenomena. So eddy currents, note, eddy currents cause increase in temperature of the surface. Eddy currents can cause increase in temperature of the surface. And if this is a copper pipe and we drop a strong magnet through it, so why this magnet will slow down inside the copper pipe, even if it is not touching the copper pipe, what will happen is when it will be passing through the copper pipe, the copper pipe will not be acting as a conductor, like a wire-like conductor or a rod-like conductor. It will be acting like a surface. So this falling magnet will be changing magnetic flux around the wall of the pipe, and this will produce different potential points on the surface of that pipe, which will cause currents that will travel on the surface. Those currents will also have their magnetic field, and those magnetic fields that are produced on the walls of the pipe, they will oppose the motion of the magnet through it, and that will cause the magnet to slow down inside the pipe. And if you have seen the video that I've shared with you, you can see that person over there, that scientist or person who was performing that experiment, he dropped a magnet through the pipe, and it took a very long time to pass a short pipe. Why? Because when magnet was passing through, it was changing magnetic flux, producing different potential points on the surface, producing currents on the surface. Those currents were producing a magnetic field, and those magnetic fields were opposing the motion of that magnet in the pipe. So eddy currents are, they sometimes you need to explain them in particular situation. So, and we'll be doing past because you'll see some questions where just mentioning these names make everything very easy. Otherwise, you have to explain the whole thing.
Sir, I have a question.
Yes.
Sir, when the magnets is getting dropped to the copper tube, yeah, we can't use the right-hand grip rule because the currents will be in random
No,
directions.
no. Yes, yes.
If it was a coil, then
And
we could.
yes, because in that case, current was supposed to go in a particular direction. The potential difference, one dimension is very long, the other dimension, the width of the conductor is very short. When we
Yes.
have a solenoid or a coil, or we have a long conductor. In that case, one direction is very long, the other directions are very short to develop that potential difference. So more likely the potential difference is developed in one direction, and that's why current goes in one predictable direction.
Yeah, okay.
Uh, in this case, if we focus on any short part of the surface, the left hand Fleming rule or right hand Fleming rule will be applied. Currents are random. Now, mm, okay, this is long magnet. This is a no. This is a magnet. For example, this side is north, this side is south, and we are passing a coil which goes which is like this, like this. There is a sensitive voltmeter here. Yeah. This is side Y. And it is moving with a constant speed. Okay, now if this is this is Q magnet, and I need a graph of changes voltage on the voltmeter. Okay. So or my micro V, which is very sensitive voltmeter. This is point B.
Sir, your screen just
Just 1 second. Yes, I think I'll just give me a minute.